Hi everybody, this is Miss Peachy from Physical Science, and today I'm going to talk to you a little bit about covalent bonding. Covalent bonding is also known as molecular bonding, so we call these substances that are made molecules. Okay, a little different from ionic bonding, lots different actually. With covalent bonding, you still need to satisfy that octet rule. You still need to make sure that you have 8 valence electrons, but it's done a little bit differently. So if you remember back from ionic bonding, in order to get that 8 valence electrons, the substance, the atom is either going to get rid of or gain electrons. And when it does this, it is able to get in a stable number of 8 in its valence shell, but it also becomes charged. So for example, sodium has 1 valence electron. And with its 1 valence electron here in sodium in this column, it gets rid of that 1. That means it has 8 valence electrons because it's got rid of the 1 and now it's just got that 8-fold set in the shell right below. But now it has a charge. It has a positive 1 charge, right? Chlorine has 7 valence electrons, and when it gains 1, it now has a full 8, but now it has a negative 1 charge. So sodium and chlorine stick together because the positive 1 will stick to the negative 1. So the bond that forms there has to do with having opposite charges. With covalent bonds, that's not the case. Neither atom is charged. We're not dealing with ions here. That's why we call the other guys ionic bonding. We're dealing just with atoms. And each atom does not have a full valence set. But to satisfy the octet rule, here, instead of getting rid of or gaining electrons, they share electrons. So here we have 6 valence electrons in this particular atom, which I think is oxygen, and 6 in this one. And 2 of them are being shared between the 2 atoms. So that gives the atom on the left 8 and the atom on the right 8. Even though neither one actually has 8, they have 6 of their own with 2 that get shared between them. And that allows them to satisfy that octet rule, but it also bonds them together. So again, this type of bond is called a covalent bond, or a molecular bond, and then this then is called an oxygen molecule. Okay? Now, some of the properties of covalent substances, they tend to be gases or liquids. These are typically 2 nonmetals that are bonded together. And so they are gases or liquids. Because they're gases or liquids, that means they have a lower boiling and melting points, right? So at room temperature, they tend to either be in a gaseous state, already having achieved their boiling point, or in a liquid state, which means they've already achieved their melting point. They're relatively soft, weak bonds. They don't typically conduct electricity, and they don't typically dissolve in water. Here are some examples of substances that are formed from covalent bonding. Here we have hydrogen, which forms a hydrogen molecule. We call this type of molecule diatomic because there's 2 atoms of the same kind. Fluorine also forms a diatomic molecule, F2. And we have carbon dioxide and carbon tetrafluoride here, which is 1 carbon atom and 4 fluorine atoms. So again, none of these are charged. They are all just sharing electrons. So to figure out kind of how they share and what type of structure forms, we use these rules. We draw these structures called Lewis dot structures, and that's what I'm going to focus on today. So there are some rules for the Lewis dot structure. Rule number 1 is to arrange the atoms around the central atom, which has the lowest electronegativity. When you look at this chart here, you can see that electronegativity decreases as you go to the left and to the bottom, with francium down here having the lowest electronegativity of all of the atoms in the periodic table. Fluorine has the highest electronegativity. These guys here, because they are the noble gases, they are not electrically negative at all. Okay. So we want to have our central atom as far away from fluorine as possible. That's the key here. Our central atom as far away from fluorine as possible. The second step is to add up all the valence electrons of all the atoms that form that molecule. For example, with hydrogen, H2, there are 2 valence electrons. So that's what we would add up. With diatomic fluorine here, there are 14 valence electrons. So that's what we would add up. Step 3 is to draw single bonds, and step 4 is to satisfy the Octet Rule, except it says for hydrogen because hydrogen only has one shell, right, with only 2 electrons that can fit in it, so it can't get 8 in there. It doesn't work for hydrogen. So we're going to do some examples. The first one is carbon tetrafluoride, which we kind of saw, or carbon tetrachloride here. I'm sorry, we saw carbon tetrafluoride a minute ago. But we'll look at this one. I'm going to do it on the tablet down below here, and then we'll kind of go through a few more examples. So first thing I want to do is to hang on a sec. Kind of aim this down at my notebook here, and I'm going to flip it around so we can see a full view and make it bigger so you guys can see the notebook view a little bit better. There we go. Alright, here's my periodic table. Here is my notebook. And we're going to start with carbon tetrachloride. And then we are also going to learn how to name them a little bit later as well. So the first step, remember, is to put that central atom as the one with the lowest electronegativity. And if you remember, on the periodic table, I highly encourage you to always write on your periodic table, doctor it up really well. But electronegativity decreases to the left and down. I don't really have a space to write it on the side, but so francium down here has the lowest. So the furthest away from fluorine. That's my shortcut. All right. Chlorine is right next to fluorine, so that one's not in the center. Carbon's further away from fluorine, so carbon is going to be our central atom here. Carbon. And then typically chlorine, we'll just draw it around on all 4 sides. We're not using the shapes or anything at this point, we're just drawing the Lewis dot structures. Okay, now I got to add up the valence electrons. Well, I like to make a little table here with all of my atoms. So carbon, chlorine, we have 1 carbon, and we have 4 chlorines. Okay. Number of valence electrons for carbon. Carbon has 4 valence electrons. Chlorine has 7. 1 times 4, a total of 4 here. 4 times 7, a total of 28. Just add that down. 4 plus 28 is 32. So a total of 32 valence electrons. 7 in each chlorine and 4 for the carbon. Okay? Alright, so 32 valence electrons. So we need to arrange these around the atoms. And you want 8 around each one. Okay, and I'm going to do this with, I think I'm trying to do it with pencil because I might need to do some erasing. But I just start by just putting them in. 1, 2, 3, 4, 5, 6, 7, 8. I'm adding them up as I go. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So it fit perfectly this time. We have 8 around each. That's the check. Do we satisfy the octet rule? Well, this guy has 8, right? This guy has 8. This guy has 8. This guy has 8. And this guy has 8. See how they're shared? So then, when we draw our Lewis dot structures, we don't leave it like this with all the dots. It's too confusing. We leave the dots, typically when we draw the Lewis dot structure, we just draw the final version just has the bonds. So wherever you have 2 dots between 2 atoms, that's a single bond. So right now we have our final will have chlorine in the middle. I'm sorry, carbon in the middle, right, with the 4 chlorines around it again. And you've got a single bond here, a single bond here, a single bond here, and a single bond here. And that's how you would draw it. You don't need to draw these electrons because this tells us that there are, when you draw Lewis dot structure, you have to have 8 around each one. So as long as your Lewis dot structure is correct, it is assumed there's going to be 8 around each one of these guys. Okay. So your final Lewis dot structure is this. Some people do like to put the dots in, but it's not necessary. Okay. So going back to the screen, this is what we have here. Notice the difference here. This picture and my picture are a little different from each other. My picture has it kind of at right angles, and this picture here, oops, doesn't. And that has to do with something called bond angles, because not always are you going to have 90-degree angles. That's something we're not going to get into today. So we'll just talk about the Lewis dot structures today. We don't need to worry about bond angles yet. Okay? So let's do another example. Another sheet on my notebook ready. And our next one, we have carbon, disulfide, and CS2. Okay, so again, look at the periodic table here. Carbon's over here. Sulfur's closer, so carbon's in the middle. It's also kind of obvious when you have like an S2 versus, that's going to be on the outside versus the carbon, but just so you know. Okay, so let's draw this guy. See. He's a little stuffy right now. So we have carbon, disulfide. We have, that would draw it like a sulfur, a carbon, and a sulfur. And then it says count the valence electrons. So let's look at our periodic table. Carbon has 4. Okay, so again I'm going to do like I did before. I have 1 carbon with 4 valence electrons. I have 2 sulfurs, and sulfur has 6 valence electrons. 1 times 4 is 4. 2 times 6 is 12. So I have 16 total valence electrons. Okay. So let's start arranging these guys. And again, I'm going to use my pencil because if I screw up, I want an eraser. Alright. So I'll just start around the outside. 1, 2, 3, 4. 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15, 16. Okay, I drew 16. Now let's see if the octet rule is satisfied. This sulfur has 8, cool. This sulfur has 8, double cool. Carbon, only has 4. Uh-oh, we didn't satisfy the octet rule, so we didn't do this correctly. Good thing I used my eraser, or my pencil, so I can have my eraser available. So, just because we're used to drawing them with 2 on each side doesn't mean that that's the only way they can be drawn. Okay? As long as sulfur has access to all of them, then they don't have to be distributed evenly around the S. So I can take these 2 guys from the top and I can plunk them there right in the middle. Okay? Now I know to do this because I've done this many times before, but you might not be as comfortable with that part. I'll take these from the top and I'll plunk them right here. And now let me check that octet rule. Sulfur has 1, 2, 3, 4, 5, 6, 7, 8. Sulfur has 8. This sulfur has 1, 2, 3, 4, 5, 6, 7, 8. This sulfur has 8. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 8. So they all do have 8. It just looks a little bit funky. What this also means is, remember that wherever you have 2 electrons between 2 atoms, that's a single bond. Here we have a single bond, but we have another 2. So we have what's called a double bond. There is a double bond here between the sulfur and the carbon. When we write this as our Lewis dot structure, then we would write S double bond C double bond S. That would be our final Lewis dot structure. A double bond means they share 4 electrons now. They don't just share 2. That's a stronger bond because, you know, the more electrons that are shared, the more those things are meshed together, essentially. So our CS2, carbon disulfide, is written like this. Okay? And as you can see in this picture, they left the little unbonded electrons out there, but you don't have to leave those. In fact, this is preferred here. Okay, so that's just 2 examples, and you guys are going to be working on more examples on your own in class today. Alright, so you can stop the video and work on your examples, and when you're done and you feel comfortable with that, come back, and then we'll talk a little bit about naming covalent molecules. Alright, glad to have you back. So we've been kind of talking about these with names, and we're going to look at how do you name covalent molecules. It's different than naming ionic compounds. So the biggest difference is the prefixes that are added. And those prefixes indicate how many of each atom there are. The prefixes are mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. And those are just the first 10. There's more than that if you go beyond 10. When you name them, typically what you do is you put a prefix on if it has a subscript. Except for, remember, 1 has no subscript at all. The only time you use the prefix mono is for the second part of the compound, or the molecule. You don't say mononitrogen monoxide, you just say nitrogen monoxide. So you don't put the prefix on the first part if it's mono. That's the only time you don't put the prefix on. Otherwise, the prefix goes on both parts. So N2O3 dinitrogen trioxide. Okay? There are some weird exceptions to this too, by the way. Hydrogen. Typically, you don't say dihydrogen, but you can. So, for example, in this picture, H2S, you would think you say dihydrogen sulfide, or dihydrogen monosulfide, but sometimes it's just known as hydrogen sulfide. So, hydrogen kind of ends up being a weirdo a little bit, but we're not going to use the weird exceptions. We'll just try to follow the rules as they're written, okay? So here are some examples here. HF, hydrogen monofluoride. The other part of the rule, of course, is that just like with ionic compounds, you drop the ending of the second part and you add IDE, okay? So instead of hydrogen monofluorine, you say hydrogen monofluoride. For H2S, instead of saying dihydrogen monosulfur, you say dihydrogen monosulfide. Okay, always IDE. Okay, so that's really important. So here are some ones for you to practice some more. I want you to kind of, again, pause the video and kind of look through these and practice them a little bit. And then go back to the practice worksheet to do more practice on naming of the covalent compound. All right, hopefully all of that made sense to you guys.